Hello. Hi, Salim.
Hello, Salim. Okay. Oops, I should.
How are you guys?
Yeah, fine, thanks. Okay, so maybe we can start. So hello everyone, welcome to this second day of this SAZERAC meeting dedicated to CMB and reionization. So today we have like 3 talks, then we have a short break, and then we have 3 talks again, and we have time for discussion at the end. So you can ask questions through the Q&A option in the Zoom, and you can also put further questions and discussion on the Slack later on if you want to continue after the talks. Just a reminder, so today the deadline for the full SAZERAC meeting, which will take place on the 14th of June. So if you want to submit an abstract, it's today. So I don't know which day or time is it, but it's kind of today. Okay, so maybe we can just start with Nikhil Gupta on deep learning method to reconstruct patchy reionization signal from CMB maps. So I leave you the floor, and you have like 15 minutes. So I try to make 1 or 2 minutes before a sign if it's needed.
All right. Yeah. Thanks a lot. Thanks for inviting me, for having me here to talk in this meeting. I'm Nikhil Gupta. I'm currently a postdoc at Astronomy and Space Science in Perth. This work that I'm going to present was partially done, well, it's still work in progress, so I'll be showing some preliminary results. Partly it was done when I was in Melbourne, and then I stopped doing things, looking for a new house and everything in Perth. And some of the results that I'll show today are related to the progress which was made in the last few weeks. So I will be talking about a deep learning method to reconstruct the patchy reionization signal from the CMB maps. So the basic idea is basically to make a network, a deep learning network, which has millions of parameters, to learn about the properties of CMB maps, and also the anisotropy that is in the maps due to the patchy reionization, and try to reconstruct the latter signal from these CMB maps. So a quick outline is that the goal is basically for this deep learning method is to, as I was saying, to reconstruct this patchy reionization signal, which is the patchy tau, the optical depth. It's the hydrogen optical depth. And the idea is basically to train these CMB temperature maps that you see in the left plot. It's one reionization of a CMB simulated map, which doesn't have noise or foregrounds or any other anisotropies, secondary anisotropies. And the idea is to use these 2 maps, put it through the network, and let the network learn the patchy reionization tau signal from CMB map. And when the network has learned the signal, you basically use the trained network to reconstruct the maps, in principle from the observations, but at the moment looking into the test maps, which I created on my own. So I will be talking about this, and I'll talk about the deep learning method a little bit, and also some of the previous examples that I've used this network on. And then I'll be talking about some, as I said, preliminary results and some future work on that. So quickly on the network, it's a encoder decoder kind of network where you input a set of maps, and then the encoding phase, which is in the red here, it basically increases the filter size and decreases the map size. So tries to look into the future, basically in layman terms, in the map at different scales. It has a window function, which is a function which moves across the maps from top left to bottom right, looking for the correlations or the features in the map. And then there is a decoding part of the network, which decodes all the information. There are concatenations of the data between the encoding and decoding phases. Each of these building blocks have several convolution layers with a window function, which I'm basically using 3x3 window function. To avoid the overfitting, there's a dropout. There are residual connections, which we found that they really help in the precision in the end, and also the activation functions, the number of activation functions that we tried, and use linear and the SALU and ELU kind of activation functions. So sorry for all this jargon, but if you are interested more in this network, we can talk offline. But I'll tell you something that really helped, which is the dilated convolutions in this network. So for each of the convolution layer, the way it works, for example, is if you see this moving GIF, on the left-hand side, the convolution window function, it goes through the image, where image is the one on the bottom. It goes through different pixels with the window function. With dilated convolution, as you see on the right-hand side of the figure, what happens is that the convolutions are dilated, as the word says. And that means that you're looking into different spatial information within the same image. So doing these, combining these different convolution layers with different dilations, we use dilation rates of from 1 to 4. Found that it really helps in recognizing the small scale and the large scale features in the maps. So some of the examples where we used these networks before, for example, we wrote a paper about estimating the masses of galaxy clusters from Sunyaev-Salzovich effect, which is, as you guys know, is the inverse Compton scattering of CMB photons by these high energetic electrons in the galaxy clusters. What we did there is basically, for example, in the first column in the figure on the left-hand side, you have these CMB temperature maps, which has CMB ionizations, the SD signal, it has noise with like 5 microkelvin arc-minute wide noise, similar to what noise you expect in the SPT pole-like experiment. Then we had 4 grounds signal. For example, the signals detected in the papers like George et al., which includes radio, dusty foregrounds. And plus there is a 20% intrinsic scatter that we include in the training set and also in the simulations that we test our network with. So the takeaway is basically that you put first 2 columns as a training set, you give it to machine, the CMB and the true SD signal, and the machine predicts from your completely different test set the predicted SD signal. And as you can see from the residual, it's an order of a couple of orders of magnitude smaller. So it's doing very well. And the plot on the right-hand side shows the estimated mass from this machine learning technique as function of true mass. And the panel on the bottom shows the basically the difference between the true and the estimated masses, which looks pretty good. So we found that the input mass we could recover with the scatters around 20%, which is really good. Given that the maps have noise and foregrounds and intrinsic scatter and everything in there. So if you're interested, you can look into this paper that came last year. Another such example that we used to detect the anomalies using the similar network with few changes, using the detecting the CMB cluster lensing signal, and from there to estimate the masses of the galaxy cluster again. So CMB cluster lensing is similar to weak lensing. It's just that here you lens the CMB instead of the background galaxies in case of weak lenses. The plot on the bottom is a result plot where again you put like very noisy maps and you give the true temperature maps to the machine, and the third column shows the prediction. And the residual again is very small, and the important thing is that even in these very noisy maps in the first column, the network is able to detect the lensing signal, which is shown in the last two columns, where the true TFF minus the true TFF is basically the true lensing signal from the lensed minus unlensed map. And the last column is the predicted signal from the lensed minus true lensed maps, true unlensed maps. So it is working very well from these examples. If you're interested, you can look into this paper also. It's the one we did last year for anomaly detections, anomalies like CMB+EOR. So this motivated us to look further into some other problems, for example, the detection of patchy reionization from the CMB maps. And to do that, we basically used simulations. We used a 21 CMB fast. It's a Python with a Python wrapper to create these beautiful light cones. For example, the light cone on the top panel is the density, and on the bottom panel is the hydrogen fraction. And this light cone goes from low redshift to high redshift, and the parameters which are used to create these light cones are written on the left if someone is interested in creating these light cones. So basically, given this density and the hydrogen ionization fraction, you can compute this optical depth using this expression, which I found in Liu et al. 2016. So you basically integrate over the redshift from 0 to the redshift of CMB, given that you have this X patch hydrogen ionization fraction and the density, in this case, the baryon density. Integrating using this equation, you get these optical depth maps for the patchy reionization as shown in the right panel. So looked into, created several of these light cones using 21 CMB pulse, and the power spectrum is shown on the right panel, and I think it looks fine given the peak is somewhere around 1000, which is expected. So we in the plot on the right hand side, I'm showing the power spectra for some 10 realization, and the purple one is just a random realization, which I kind of highlighted in order to see that what will happen for a similar kind of for the same realization when we are using our trained network to predict this tau map. So the network and the data that goes into the network is basically that we have this temperature maps, the CMB temperature maps. At the moment, these are the noiseless maps. And together with the optical depth maps that are created using the 21 centimeter fast, Using this expression, very simple expression, the exponential of minus tau, we get these very small anisotropies into the temperature maps as shown in the very right plot. So as you can see that these don't really change by eye. You can't really see anything changing in the resulting CMB map because of these the patchy ionization signal into the CMB maps. I think that's expected. So what we do is basically generate something like 5,000 simulations with 4 times 4 degree squared cutouts and several random realizations of CMB and patchy tau maps to create a training set and give it to the machine to learn these patchy tau signal from this CMB map. So by eye, it seems that it's not possible, but let's see what the machine can do. But I think I also wanted to say a little bit about the very important part of this machine learning, which is the pre-processing of the data. So if I give the top 2 maps, the temperature and the exponential of the minus tau maps to the machine and expect it to learn futures through that, the machine won't be able to do that because you really have to pre-process your images before they go into the machine. So I think I spent several weeks in order to understand that what would be better. There's a lot of trial and error include. But given that the scale, as you see on the top right panel for the optical depth map, it's very, very small. It's between 0.96 to 0.98, and the machine was not able to understand anything given that very small scale in these maps. So the trick was, in the end, was to increase the contrast for these maps, as shown in the bottom panel, with a contrast factor of 50. You can see now the map has a range between 0.5 to 1.4. And also for the CMB maps, tried to put it into digits of between -3 to +3 using a constant factor. So this did the trick. And here are some results. So what you're seeing here is in the first column, you see different realizations of the true tau signal, which was added to the CMB maps. And once the network is trained and use the test set, which is untouched, you create this reconstructed, it reconstruct these tau maps as shown in the middle panel here. And the rightmost panel, the third panel here, is the residual, which is again like it's almost like 2 orders of magnitude smaller. So it seems that the machine is able to understand and learn this tau signal which we added to the CMB map, which is really encouraging. But I mean, so this basically shows that you have a CMB map where signal is dominated by CMB. You add a very feeble signal from the tau maps, and the machine is still able to see these features and predict very good tau maps from that. Looked into the power spectra from these reconstructed map. For example, the left panel is again still the input training sample, the correlation function from that. And the right panel shows the reconstructed power spectra from a test sample, which is untouched, which machine didn't see when it was training. And I basically the purplish line on the left-hand side is same realization, but I basically didn't put it into the machine when it was training, and when it predicts, you can see the shape is very similar from these reconstructed maps for this power spectra. And it works very well at 0 microkelvin arc-minute noise levels for the CMB maps. But when I tried basically to add some white noise into the CMB maps, you see that the amplitude is slightly smaller as compared to the true amplitude, as you see in the power spectra curves with the 1 micro Kelvin arc-minute notation. So,
Nigel?
Yep.
Less than 1 minute, please.
Sure. So I'll basically conclude. I think it seems that the deep learning method that we used in several other problems before, it's also working pretty well for reconstructing this patchy tau signal. But the caveat is that these maps are noiseless, and when we add a little bit of noise in the maps, the signal is a bit smaller as compared to the true signal. I showed you how I created these maps and how the deep learning network is used to estimate the patchy ionization signal from these. The power spectrum from the reconstructed maps, they look pretty good as well. But again, there are several things. The CMB maps don't come noise free. There is noise in those maps. There's lensing, large scale lensing in the maps. And also there are foregrounds. For example, the plot on the right hand side shows the CMB in the blue, and in the red, these are the foreground signals due to the radio and dusty and other sources taken from the geospatial. And the green one is basically the 5 microkelvin arc-minute noise, which is the noise level for current experiments like SP poles. So future work has a lot of things that can be done here, and yeah, but the method looks quite motivating and should be looked further. Yeah, I think that's all from me.
Okay.
Thanks.
Thank you. Any question on Zoom or on the Slack? Just checking on Slack. Just have a quick question on the SZ reconstruction, because I'm interested in this part as well. So you find the residual is like 1%, but still it's always negative. Do you have any hint of why the residual is always negative in the center?
So you're talking about this fourth column here, right?
It seems like
I think
the center.
Yeah, I think it's just the visibility here, but the number goes from 1 times 10 to minus 8 to -2 times 10 to -7. So it is between positive and negative.
Okay.
Yeah, I think this is just the bar for the color plot.
Okay. There's one question is, what are the differences between your approach and the one presented yesterday by Eric Guzman?
Yeah, I think I saw Eric's paper, and so I'm not. I think the one difference is that he was doing it with the Q and U maps of polarization signal, and there you don't really you don't worry about the foregrounds a lot in the polarization, but with the temperature maps, which is still the future work I want to do, which is one of the things that we need to consider, and the lensing as well. I think the network is a bit different also. As I showed, the dilations, they really help in the end. Without dilations, I think I saw in the beginning, probably last year, a lot of bias in the construction of these power spectra. Other thing is maybe the pre-processing, which I thought that I mean, our pre-processing is a bit different, and that really affects a lot in the end. Because if I don't do pre-processing as I did by increasing the contrast for the tau maps, the deep learning network doesn't learn anything. So I think that's the problem I was dealing with for a few weeks, and probably few things more can be done with the pre-processing here.
Okay, thank you. Sorry, you have to move on to the next talk. Thank you, Nigel. Yushan, if you can share your screen.
Yeah, can you see the screen and hear me?
Grace, yeah.
Yeah, okay. Go away. All right, so okay, I'll just get started. But before I get started, I also want to thank the organizer for giving me this opportunity to present our work. So for those who don't know me, my name is Yuxiang Qin. I'm a new associate postdoc at the University of Melbourne. And today I'm presenting another realization inference work that I did with Andrea Messinger when I was in Pisa, Italy, together with other collaborators such as Vivian Pulling. So this work, in this work, we focus mostly on using the CMB observables to infer the reionization history, as well as the property of the galaxies that are believed to have driven reionization. All right, so a quick introduction. So during the reionization, we get more free electrons, and this led to increment in the large-scale CMB power spectra. Therefore, by observing the CMB polarization, we could actually use this large-scale correlation to infer the free electron number density at a high redshift. Of course, you can also do it with the B-mode polarization, but the signal will be much weaker. That's why we are focusing only on the large-scale E-mode polarization here. So what has usually been done when analyzing the CMB data is that we use a hyperbolic tangent function to assume to represent the reionization history. And this function can be well described using just two free parameters. One is the timing of the transition from a neutral universe to a ionized universe, and the other one is basically the duration, which in most cases are actually set to be a constant. So by varying these two free parameters and compare the inferred power spectra against the observed one, so we could actually find the best model which provided us with this evolution of the free electron number density. And using this number density, we could also infer the CMB optical depth, like what Nick just presented. But here I'm just focusing on the globally averaged quantity. And this optical depth, which is often used as an input constraint to UR simulations. By that, I mean when we run UR simulations, instead of keep forward modeling the E power spectra and compare it against observation, we actually just try to keep the predicted UR history consistent with the inferred optical depth. So this naturally raises one question. So is the optical depth unbiased summary statistic? So basically this optical depth is one quantity represents the integrated reionization history, but the power spectra would give you more information about how the number density of the free electron evolves. So the second issue that in analyzing the CMB data comes from the assumed tangent function. So most UR model nowadays actually show the process of reorganization is not a tangent function. So in particular, it has a extended tail towards high redshift due to early star formation. So for instance, here I'm showing you a plot from Miranda et al. 2017, where they explored 3 different physically motivated reorganization model. Basically, the UV outline photon dominated by POP2 or POP3 star formation. And they model the E-mode power spectra and compared against the measured power spectra from Planck back in 2015. And they actually find that compared to the tangent model, this physically motivated UR model actually fit the power spectrum much better, which can be seen here from the reduced chi-square. And the other thing they also find is that it seems that Planck 2015 data actually favors earlier contribution from POP3 star formation, which sets this very high level of ionization. So exploring different reorganization-based function has become quite popular in the past years, including the Planck team themselves. So in 2018, they actually explored many different base functions rather than just the tangent function. And they also show that when you change the reorganization model, you also get very, well, not very different value for the optical depth, but you do get a different value. This is also what Miranda et al. Found back in 2017. So this comes to our second question. So, so basically, even if the optical depth is a unbiased summary statistic of the CMB measurement, is the assumed tangent model well, a good representation of the reorganization history? So, so this comes to our work. So we use 21 centimeter fast. Nick just showed some results for his work, but basically we model the average property of galaxy and we parameterize them as a function of their halo mass. So in this work, we mostly focus on properties including the stellar to halo mass ratio. So there are 2 free parameters govern this relation. And we also have free parameters tell us about the UV escape fraction. And this movie, some of you may have already seen it many times. This is the 21 centimeter brightness temperature light cone. But for this work, we only focus on the EOR area. And you can see that by varying these astral parameters, we get a very different EOR signal and also morphology. For some parameters, we could even link the model to galaxy observable, which is shown here as the UV luminosity function. So we could also use these observables to constrain the model. And 21 centimeter fast is very efficient in producing the EOR history. Therefore, we could actually run MCMC to explore the parameter space. So here I'm just, again, showing you a movie demonstrating the process of MCMC constraint, but for another work. This is using the 21 centimeter power spectrum from MOC observation as the input constraint, in addition to some other constraints. But basically in this work, we are replacing the 21 centimeter power spectra using the CMB observables, such as the EE power spectra and the inferred optical depth. All right, so to do this work, we actually have to extend 21 centimeter fast. So we include wrapper to collect 21 centimeter fast with the class package, which means that we use 21 centimeter fast to infer the UR history. For example, this is density, this is photon ionization rate, this is the neutral hydrogen fraction. And then we pass the UR history to class and calculate the CMB power spectrum. And then, well, for example, on the right side panel, this is showing you some power spectra that we actually calculated from the CARS package in comparison to the measured data from Planck in 2015, as well as 2018. And then we give this power spectra to the Planck likelihood code to calculate, this allows us to compare our modeled power spectra to the actual observations. And this is basically where we get the chi-square during the MCMC. Basically, this type of simulation, we could do 100,000 simulation for Y inference. All right, so I'm gonna show you some results. So firstly, I actually want to tackle the second question. So is the tangent function a good representation of the realization history? So here I'm showing you two inference results using the same CMB observation. So here we are forward modeling the E power spectra and compare against the Planck 2018 result. So on the top, I'm showing you the posterior of the inferred E power spectra. So basically there's a 1 sigma and 2 sigma area, and the yellowish color shows you the tangent, shows you the inferred power spectra if we use the tangent function, and the purple line indicates what the result looks like if we use a physically motivated EOR model such as 21 centimeter fast. So you could see that when the model is constrained by the input E power spectra, we get the inferred E power spectrum from both models look basically identical and well constrained by the observation. However, if we look at the EOR history, which is shown here as on the bottom left corner, you could see that 21 centimeter fast does support a extended tail that shows a higher ionization rate at high redshift. And because of this early star formation, we actually predict slightly higher optical depths compared to what the tangent function suggested. So the conclusion is the tangent, comparing to using a physically motivated EOR model, the tangent function does slightly underestimate the optical depth, but still the uncertainty is is relatively very large, and which means the difference is still consistent within Y sigma. However, the inferred EOR history are very significantly different between two models. And the second result I want to present is actually from 3 inference results. This is to answer the question whether, under the circumstance that we are using a physically motivated EOR model, does using the optical depth lead to biased inference when you do EOR modeling? So here I'm showing you 3 inference results. Again, the brownish region shows you a MCMC result where we only consider non-CMB observables. So this includes what we call the dark fraction. This is a neutral hydrogen fraction upper limit at redshift 6 measured from the quasar spectra. And we also consider the luminosity function. Sorry, I should say that this is using 21 centimeter fast model rather than the tangent model. And then on the top of that, we run a second inference. We will show you the second inference result, which we forward model the E power spectra and compare against the Planck result, which is shown here as the blue curve. As you can see that when we include information from CMB, we remove a lot of model that otherwise shows very high power at this large scale. And this model often have very early ionization as well as very high value of the optical depth. And the third inference result shown here as the red curve shows you what would we get if we use the optical depth rather than forward modeling the E power spectra. So immediately we could see there's essentially no difference between the two results, which is the blue and the red. So apart from maybe we are excluding slightly more models which has earlier ionization if we use the optical depth. However, the conclusion is that comparing to using the EE power spectra, we think, we find that using the optical depth does not lead to any bias in the inferred EOR history. And this is.
You have 1 minute.
Yeah, I'm almost done. So this seems to be opposite to what have been found in Miranda 2017. So and we just reanalyze the same model that they presented, but we compare against the Planck 18 data. And if you look at the chi-square difference again, you could see that now the Planck data doesn't actually prefer the early ionization. So this is because, well, this is mostly because of the reduced power at L around between 10 to 20. So the power is actually reduced. That's why we do not actually see any preference of early star formation from the Planck EE power spectrum. So before I conclude, I just want to advertise an ongoing project by our PhD student Ivan. He is trying to include fold modeling of the kinetic Sonian-Zadovich effect, and we will be trying to use the KSZ measurement, the KSZ power spectra, to further put some constraints on the UR history. I will leave you with my conclusion here, but emphasize again that our physically motivated UR model suggests that the optical depth is slightly higher than what the tangent function suggests, and this is the value that we are trying to advertise. Okay, thanks.
Thank you very much. Time for a quick question. Anyone? So let's check again. I just had a technical question. How long does it take to make your 500,000 model with 21?
Yeah, so it depends on the model that we choose for this work. So each model would only take like 20 minutes. That's like 0.1 million simulation would just take roughly 30,000 CPU hour, and if you distribute it with MPI job, it can be finished within like 2 weeks.
Okay. Okay, so I guess we have to a question on Slack, it seems. Sorry. So there's a question by Yunbei. Can 21 centimeters per fast do self-regulated regulation, ionization?
Sorry, he is actually here. We could actually discuss it now, but I actually, so we do have feedback, but this is not included in this this current result. So the feedback is modeled as a free parameter. So in this sense, you could say that even the feedback is also driven by what you provided as a constraint.
Okay. There's another question on Slack, but I'll leave you answer directly on Slack so that we can move on to the next speaker. Thank you very much. Now the next speaker is Yunbei Park on post-ionization KZ signal from illustrious simulation. When you want, you'll
okay.
15 minutes.
Thank you. Okay, you hear me, right?
Yes, perfect.
Okay. Yeah. Okay. I'll begin. So I'd like to first thank the organizers. I have not seen so many case talks in one conference before. So yeah. So today I'll be talking about post-ionization case signal from the illustrated simulation. I'll share the insight I got from this work. So let's see. Yeah. Okay. So I guess people talked about introduced KSC multiple times already, so I'll keep the intro brief. But it's basically a secondary CMB anisotropy induced by the Doppler shift of photons scattered by ionized gas along the way. And we currently have this constraint from SPT, which says at L of 3000, it's 3 plus minus 1 microkelvin squared. So yeah, basically the temperature change from this KSG is given by the line of sight integral of the line of sight velocity component times the optical depth of the ionized gas. And basically the optical depth is given by the Thomson scattering. So you can pull out all the physical constants we know, and then you can define this ionized momentum field Q, and then you only need to model this part of it, the equation. So basically the C of L for the KSC is given by the line of sight integral of the momentum power spectrum P of Q. And there's this perpendicular sign that says it's only the curl mode that contributes to the signal, because the divergence mode gets washed out in the line of sight integral. So there is a convenient standard expression for this momentum power spectrum, which expresses it in terms of density and velocity field. I'll kind of walk you through the derivation very quickly, because this is kind of needed to explain my result later. So basically Q is expanded to V plus delta V, and then in the Fourier space, the delta V, the product becomes convolution. And in the curl mode, you can ignore the first order term V, because in the linear regime, the velocity field does not have any curl mode. In the nonlinear regime, it's subdominant. So in any case, you can ignore it. Then in the power spectrum of Q, the derivation involves this fourth order term coming from squaring the second order term, basically. And then there's this Wick's theorem, which allows you to break this fourth order term into 2 second order terms, as here. And then one of them becomes density power spectrum, the other becomes velocity power spectrum, which is basically what you're seeing here. So you can forget about the complicated geometrical factor in the right, and basically in the left, it says it's convolution of density and velocity power spectrum. And yeah, it roughly goes as velocity variance multiplied by the electron density power spectrum. So when you're modeling the KSC, it's mostly about modeling the electron density power spectrum. And the post-reionization and reionization signal, they are subject to different kinds of physics. In the reionization epoch, the fluctuation is dominated by the fluctuation in the ionization fraction of the inhomogeneous reionization, which was discussed multiple times by previous talks of this conference. And today I'll be talking more about the post-reionization contribution, which is basically subject to nonlinear growth of structure and baryonic physics in the gas density. In the literature, it appears people are mostly quoting this number from Shaw et al. 2012, which is something like 1.4 microkelvin squared. So I thought several years ago, I thought maybe it's a good idea to maybe try to update the number by calculating the KSC signal from the state of art simulation at that time, which was the illustrated simulation. It's cosmological simulation in a 75 megaparsec box with almost 2,000 cube particles. And it's got all the baryonic physics like star formation, age and feedback, which is relevant to the post-reionization KSC. So basically, I download the particle data, create density field, the free electron density field, and then take the power spectrum and evaluate this standard expression for the momentum power spectrum, then integrate the momentum power spectrum along the line of sight to obtain the KSC signal. So in the right panel, I'm kind of showing you the overview of how the KSC signal accumulates over the redshift. Is
We lost the sound of Yunbei. Yunbei?
linear regime.
Yeah.
Okay, I'll continue. The blue case is the nonlinear regime I obtained using the halo fit density power spectrum. So basically, you see a huge enhancement in the signal coming from the nonlinear growth of structure. And the result I obtained from the illustrated simulation, which includes both nonlinear growth and the baryonic physics. So you see the enhancement from the nonlinear growth is mostly cancelled by the baryonic physics. So by taking the ratio of electron density to the dark matter density, you can kind of get the idea of how the baryonic physics is or suppressing the signal. So basically, if you look at the ratio of the spectra, you first see there is a global suppression for all wave number, which in this case about 30% for any redshift. And this comes from the fact that not 100% of the gas goes into the ionized gas in the IGM. Some fraction of it gets locked up in stars and galaxies. And because the stars and galaxies are in the overdense region of the universe, there is an anti-bias in the electron density power spectrum, which suppresses the entire value by a certain factor, less than 1. So in our case, in illustrates that ends up being 30%. It's known that the result from Shaw et al. Is overestimating this suppression because their simulation has this known problem of overcooling and too much star formation. And then if you look at high K, small scale, at low redshift, there is extra suppression coming from the supernova and AGN feedback, hitting the gas and wiping out the small scale gas density fluctuations. So in the illustrious, this ends up being extra 20% suppression. But unfortunately, illustrious is known to exaggerate the AGN feedback. So probably this is a little bit, this suppression is a little bit overestimated here. So, and then on top of the baryonic effect, there is another effect which is not accounted in the standard expression I introduced earlier. So if there are two ways of calculating the momentum power spectrum. You can generate momentum field and then directly Fourier transform it. Whereas, and then second, you can calculate the density power spectrum and velocity power spectrum and evaluate the integral in the right-hand side. So if this expression were exact, then these two results should exactly agree, but it's not the case in the nonlinear region, I find. So for example, if you go to low redshift, like ratio 0.5 and at very high K, you see that the signal can actually, there are up more than 40% extra power, which is not accounted in this expression. So when I first found this, I struggled a lot to figure out where it came from. Eventually, I went back to this derivation and found that at this step where I used the Wick's theorem to expand this first order term into second order terms, it assumes that all the fields, the deltas and v's in the bracket should be perfectly Gaussian. If not, then there's another extra term called connected moment that adds extra power to the power spectrum. So in the case of dark matter momentum field, where all the non-Gaussianity comes from the nonlinear growth of structure, you can derive this connected moment analytically using perturbation theory, which I tried in 2016. So I expanded this equation to next to leading order and derived the next to leading order connected moment after some painful derivation. And after another painful evaluation of this crazy integral, I found that this next to leading order term really explains some of the extra power you find from the simulation up to certain wave number. Of course, for higher K, at some point, there is a higher order effect, which you cannot completely explain with the next leading order. But I think this result really proved that this discrepancy between the standard expression and the simulation really come from this connected term. So if you integrate this connected term along the line of sight, it ends up being only 6% of the total signal, which is kind of disappointing. And the reason is most of the signal comes from above ratio 1, where this connected term is relatively small. But I think this 6% fraction may be underestimated in my result because the contribution below ratio 1 is kind of underestimated by too strong AGN feedback of the illustrious, and probably also illustrious has some small box size, which may be missing some of the coupling between large scale velocity mode and small scale density mode, which also should contribute to the connected term. So a little bit deviating from the main point, but this connected term appears to be important in the apocal reionization signal as well. According to this work by Marcelo Alvarez in 2016, he also finds that there is almost 40% extra power on top of what he can get from this standard expression, which goes into the apocal reionization signal. So if you're using this expression to model the KSC signal, you really need to be aware of this connected term issue. So yeah, coming back to the main point, if you compare my results for LO 3000, 1.4 microkelvin, to the results from other works, the results from other works they usually give larger signal, somewhere between my result and my results from the pure dark matter, where I completely ignore the baryonic effect. So it appears that really the baryonic physics is kind of exaggerated in Illustris, and same goes for Shaw et al. So looks like the actual KSC signal is somewhere in between 1.4 and 2.8. So yeah, so I'll summarize. But basically, I tried calculating the post-realization KSC signal from Illustris. Unfortunately, the baryonic physics, the baryonic effect seems to be a little bit overestimated. And I think it's meaningful to keep computing KSC signal from state-of-art simulations to get a better consensus on what the signal is really, to constrain the epochal realization signal better. That's it. Thank you.
Thank you very much. Any question for Yunbei? Check. Slack, no. Okay. Yeah, Adevi, got a question? Thanks.
Yeah, I do have a small question. Thanks for the talk. I was wondering, so you find a difference between the signal you measure directly from the simulation with the one you find analytically. But I see in the final tables that you've shown that the size of your simulations are quite small as well. So I was wondering how much you think comes from these connected moments and how much of the difference comes from the size of the simulation, because when you do things analytically, then I assume you don't restrict yourself to the size of the box, and the K range is covered by the box.
Okay, so not sure I understand your question perfectly, but I cannot give a good answer for how much is missing from this limited size of box, because I until I actually take another simulation with bigger box and do the same calculation. So, but looking at other works, like if you look at Loncarelli et al. 2017, they're like almost twice bigger than our simulation. I think even with the baryonic physics, it's kind of difficult to explain. So there must be some connected term which is maybe much larger than I find in my work added to this. That's my guess.
Thanks.
Thank you. Some more on the Slack if you want or need to discuss about this.
Okay.
So we are already late after half a session. So I propose that we break for 15 minutes now, if it's okay for the speakers of the second session. So we have a small break now, and we resume in 15 minutes, quarter past, if it's okay. And so talk to you soon. Okay. Final session. And we start with Atrideb Chatterjee on Cosmo MC package for estimating cosmological parameter and astrophysical parameters.
You can hear me?
Yes.
And you can see the slides as well, right?
Yes.
Oh, okay. Let me know when I will start.
Yeah, you can start now, I think, and
No?
you have
Okay.
15 minutes.
Okay, yeah, thanks. Give me just a minute. So hi everyone. First of all, I'd like to thank the organizer to give me an opportunity to present my work here. And this is the work that I have recently done with Tirthankar Roy Choudhury and Saurabh Mitra. So we have developed a pipeline or a software package called Cosmo MC, which estimates which is a parameter estimation package, and it uses the MCMC approach to do so. So let's start. So as it has been mentioned several times in this conference and has also been known very widely that the CMB photons interact with the free electrons that are available in the IJ, and as a result of which the imprints of this interaction comes in the CMB power spectrum. And it has also been done routinely that using this observation and with some kind of a reionization history, one can compute the Thomson optical depth tau. And once you calculate this tau from the observation, it can then be compared with the prediction from a reionization model to constrain the free parameters of the model. So in one hand, you have the tau estimated from the observations, and in one hand, you have the tau which you have calculated from your own reionization model. And now you are trying to compare these two tau to constrain free parameters. However, there is a catch. The catch is that in principle, the calculation of tau should depend on the reionization history one uses. For the observation, usually Planck uses the tan hyperbolic tau, tan hyperbolic reionization history, whereas the reionization history that one is using is different from this tan hyperbolic, which means that the tau has been computed from two different reionization history, and hence the comparison is not fair. So, and it has been known for a while in the literature. And to overcome this problem, one way to overcome this problem is to connect the reionization model with a CMB anisotropic code like CAM or class, which are available in public. And then feed the reionization history coming from your model to the CAM code or the class code, and therefore constrain cosmological and astrophysical parameters simultaneously. The astrophysical parameters will come from your model, and the cosmological parameters are there already. So this is like one goal of our software package. And the second part, which is also very important, is that we have people have noted that when we calculate the 21 centimeter signal, and by 21 centimeter signal I mean the global 21 centimeter signal, when we model it, it depends on cosmological parameter. To demonstrate this effect more clearly, I would like you to look at this plot. So in the x-axis, I have plotted the redshift, as you can see over here, and in the y-axis I have plotted which is called the observable of the 21 centimeter signal, and it is sometimes called the brightness temperature of the 21 centimeter signal. And now what we have done here in this, so you can see now two curves, one is the red and one is the violet. So for these two curves, I have kept all the other parameters related to 21 centimeter fixed. The only parameter that I have changed over here is that the sigma 8, which is a cosmological parameter. And as you can see, for two different values of sigma 8, one is 0.81 and one is 0.76, the curve varies substantially. And it is easy to explain why this is the case, because if we use a sigma 8, which is like higher value of sigma 8, that means the structure formation happens early in the universe. As a result of which, this dip, though I have not gone into the details of this signal, just let me tell you that this dip kind of probes the timing of the structure formations in the universe. So now, given that your sigma 8 is high, that means the structure formation will take place at earlier redshift. As a result of which, you will get your dip in the signal at such redshifts. Now that you have reduced your sigma 8 to a 0.7 to value of 0.76, you will find that the structure formation has been delayed, and the absorption dip in this signal will happen at some later redshift, as you can see at redshift 18 here. So this is the thing, that the calculation of 21 centimeter signal does depend on the cosmological parameter. And now moving on, I will first describe the package that we have developed, which is called the Cosmological MC. First of all, this code is written completely in Python because Python is very readable code. So the Cosmological MC comprises of a theoretical model which has 3 blocks. One is the CAM block, which has been taken from the publicly available thing. The reionization is taken from this paper, 2005 paper, and this 21 centimeter signal code has been developed based on the model given in this paper. So you can see that. So I have tried in the right hand side of the slide, I have tried to put a flowchart diagram of this package. So as you can see, there are 3 blocks. One is the reionization, one is the CAM, and one is the 21 centimeter model. So in the user interface, you can only put the free parameters, and by free parameters, I mean 3 categories of free parameters. One is the cosmological that you know, for example, H0, omega B, omega C, and so on. The reionization, reionization free parameter, which is the free parameters of the reionization model, which I will come in a bit. And again, there will be some free parameters which comes from 21 centimeter signal, which I again will come in a bit. So now that you have given all these free parameters, the code will take these free parameters and then categorize it and give it to the blocks that is required. For example, it will give the Cosmo and like the reionization free parameters to reionization block and so on. And once it gives it to reionization block, the reionization block will produce its own reionization history, and that will be fed into the CAM code. And similarly, the reionization code will produce the star formation rate density for both POP2 and POP3 stars, because we consider both the population of stars. And then it will feed it into the 21 centimeter model. And once this is given, the 21 centimeter model will calculate the delta, brightness temperature. The reionization will calculate 2 things. One is the gamma pi, which is the photoionization rate of H1, and another is called the Lyman limit system. By Lyman limit system, I mean the systems in the IGM which are so dense that they will remain neutral even if the whole IGM is ionized. That's what I mean by Lyman limit system. And then the CAM will produce the cells. Once these observable are given, now they would be compared with the observations that are already there in the literature, and then it will run an MCMC. And we will check once in a while whether the MCMC run converges or not. For example, we will do an autocorrelation test to check if the chain converges or not. If the chain does not converge, then we will repeat the cycle. And if the chain does converge, then we will go and do some more post-processing. And when I say 21 centimeter observations, I meant the observation data we will use here is the AGES detection. As you are probably aware that AGES in 2018 has discovered the 21 centimeter signal. And for the MCMC package, we have extensively used a package called EMC. This is also again a publicly available MCMC package. So that's basically the idea behind developing this package. Okay, so now I will take you to the parameter space. So as I have already mentioned, so in this case, we will use like total of 12 parameter if I count it properly. So one is the cosmological parameter, which is given here as this H0 omega B, as you are all aware about. This theta R is the reionization parameter, and this by reionization parameter we put 2 parameters free. One is the escape fraction and one is the lambda 0, which is again a free parameter of the model. Now, whenever you see a subscript or superscript 2 or 3, it means the contribution coming from either POP2 or POP3. Here I mean the POP2 contribution. And when it comes to 21 centimeter modeling, it becomes a little bit tricky, because when you want to model 21 centimeter signal, you have to take into account different parameters, and there is no way to escape it. So for example, though I did not go into the details of which parameter to use, but the main problem is that when you want to model the 21 centimeter signal, as it takes place in higher redshift, and there is no more observations in this, you have to have taken into account different uncertainty, and all this uncertainty will be captured in different parameters. For example, FR will take care of the uncertainty coming in the radio in calculating the radio flux. For example, you also have to calculate both X-ray luminosity and the Lyman alpha luminous Lyman alpha flux. And for that, you need to take into account different parameters that you can see here. And again, we will fix some parameters. These the which parameters to be fixed has been determined in earlier paper by our group. So that's the parameters that we kept fixed. And given that you have these three parameters, you have to compute the likelihood. For Planck, we have taken the Planck likelihood from the Planck likelihood data. For reionization and 21 centimeter, we define the likelihood like this. This is a standard way of defining the likelihood, where you will calculate the observed signal, and then you will subtract the observed signal from the theoretical modeling, and then you will calculate this likelihood. And on top of the three observations that we use, for example, one is the Planck observations, one is the Lyman limit system observation, the 21 centimeter edges signal, and another is the photoionization rate observations. On top of that, we will use two constraints. One is that the reionization must be completed at redshift 5.3. This comes from the constraint of Lyman alpha data, Lyman alpha optical depth fluctuation data, which has been shown in these two papers. And also we will use the upper limit on the neutral hydrogen fraction that comes from the dark fractions in quasar spectrum. So these are the constant and these are the free parameters that we will use. And I have already mentioned the observable that we have used, observations that we have used here. And the first thing to check whether the code works or not is to look whether our best fit model is closely resembles to the observation. So let's look at this card, and I will request you to look only at this best fit blue card. This blue card, and as you see, this is the, for example, these are the different observations that we use, for example, the Lyman limit system, and you can see that the best fit parameters, like the best fit, the card produced from best fit parameters indeed resembles the observation. It matches well with the observations in all the cases. And these black like error bar data are the observations data that we have used in our code, and that's what you will find here. Okay, and so this is so far, this observation is related to the reionization, and next we will come to the observations of like the 21 centimeter signal. And as you can see, the black curve here basically tells you the observation that has been done with the edges. This is like the observed scenario here, and our model produces this kind of curve. And as you can see probably clearly that our theoretical model cannot produce the flat bottom signature of these of the observed signal. And that is because we realized that to do this, we have to take care of the modeling more, like we have used a kind of a simpler model, but we have to take a more complex model to take care of this flat bottom. So it is true that our model cannot produce the flat bottom of the edges signal. However, one thing, so that is the thing here. So now I will go to like the next part where we want to see the constant and cosmological parameters coming from different analysis. And I want you to like notice two things. One is the contours shown here in green, and one is the contours shown here in blue. Okay, and now as you see, this green contours has been like observed only when if we use only the CMB power spectrum, nothing more, only CMB power spectrum. However, when we take into account both the reionization observations, the constraints, and the 21 centimeter, what we have got is this blue curve. And as you can see, this blue curve, the constraint on tau and sigma becomes more tight when we use a different set of parameters. However, I want to mention that it is mainly the quasar data or like the reionization data that gives rise to these tighter constraint on tau and sigma. However, this 21 centimeter, unfortunately, when we add the 21 centimeter data, it does not do much in terms of constraining the cosmological parameter. However, this 21 centimeter data, when we use, we found that the POP3 contribution becomes necessary. If we use only see, sorry?
You got 1 minute.
Yeah, I'm almost done. Okay, so when we use 21 centimeter data, we see that there are contributions from POP3 stars as well. So what the conclusion would be to the reason we get non-zero value of POP3 stars is because we add this 21 centimeter data. And this leads us to the summary of my talk. So here we have introduced an advanced MCMC based parameter estimation package called CosmoReIon MC. where we connect a reionization model with CAM and vary both the cosmological and the model parameters simultaneously. And what we have found is that we get more tighter constraint on tau and sigma 8. And for the first time, we include global 21 centimeter observations along with the other observations. And cosmological parameters do not change significantly when 21 centimeter signal is included. Thank you. Yeah, I'm done.
Okay, thank you very much. Are there any questions on the Slack or on the Zoom? I just missed one point. Is your definition of lambda 0 in your audio parameters?
Okay, so just let me, yeah. So this lambda 0 will come when you will calculate the Lyman limit, like DNLL digit. When you want to calculate the Lyman limit system, you need to calculate the mean free path of the photons. And while calculating this mean free path, you have to take into account some kind of uncertainty parameter, which is given here as lambda 0. Okay. Which appears here somewhere.
Okay. Right. I think we have to move on. A question on Slack. So what would be the additional physics you'll be used to explain Edge's results?
So for taking into account the additional physics, I have used an excess radio background, which has got some observational support.
Okay. Thank you. More on Slack on this subject. Thank you very much. And we move on with Isabella Paola Carucci
Yes.
on galaxy luminosity function to the Thomson scattering optical depth. And if you can set your slides.
Okay.
And
okay.
Okay.
Can you see my screen?
Yeah, perfect.
Okay. Yes. Okay. Hello, everybody. Thank you, the organizers, for giving me the chance of talking about my work today. I'm not a CMB person, so I'm learning a lot with these talks about KSZ and so on. So I will focus on, let me move this around. Okay. I will focus on constraining reionization histories using the Thomson scattering optical depth coming from CMB observation together with other probes like the galaxy luminosity function of this redshift. And I will maybe say something about dark matter. I say maybe because, so historically we started this work with the idea of constraining dark matter models, but at the end we found surprisingly that the dark matter model is not so important after all. But we did learn things about reionization, which is worth to tell you about. So this is as an introduction. I put here the schematic way of describing reionization. We start from the neutral intergalactic medium to the fully ionized one. We don't really know the details of how it happened. A lot can like the CMB can tell us a lot because of course the IgM, when it's ionized, it means that there are a lot of free electrons around that interact with the CMB photons and produce the effects that people have discussed so far. But of course, also the first galaxies can tell us a lot about how the whole process happened, because they are the ones responsible for the reionization to start. They produce the ultraviolet photons that are actually capable of ionizing the surrounding intergalactic medium. And so, indeed, this is the schematic, like the outline of this project, of this work. So we started with the data of the luminosity function of the high redshift galaxy. So actually we calibrated a simple EOR model with data coming from the Hubble Ultra Deep and Frontier Field. So once we had this calibrated model, we predicted EOR reionization history, and we tested these predictions against the Planck DSPT CMB data and the Edge's 21 centimeter global signal data in order to see if our models were predicting correctly what went on during ionization, and also if we could discriminate among models. because the whole thing is embedded, as I said, in the dark matter model we live it, the scenario we live it. And so it does play a role also on how EOR happened. So this is the first time in this meeting that somebody's telling you about dark matter models. So I decided to have a very quick detour on dark matter. So under the large scale structure point of view, this is the main dark matter probe that like observable that we have, no? The matter power spectrum. So the amount of clustering as function of the spatial scale of the clustering. It's really well probed and constrained by different bias tracers. So we start with the CMB at very large scales and we go down, passing through galaxy lensing clusters and so on, down to the Lyman alpha. So a huge range of scales that has been probed. So basically all the dark matter models that are out there actually need to agree to this overall power spectrum, where actually the models start to behave differently one to each other is at this really small scale end of this plot, where there are different effects that here I call dissipative effects. It really depends on the model, but basically it can be because the dark matter is not perfectly collisionless, or it has a little bit of self-interaction with each other. So different models predict a different way of actually having a cutoff in this, like a power suppression in this matter power spectrum at the small scales. The shape depends on the model, but the effect is always there. And so basically, in order to discriminate this model, we should really be able to go and check what kind of suppression we have at these small scales. And it's hard to reach these scales without having to deal with baryonic effects and so on. So to give you a picture of what is going on in different models, for instance, here is on the left, we have a perfectly cold dark matter snapshot of a simulation. So the color is the density contrast, and on the right, another non-cold model. So you can see by eye what this cutoff in power spectrum means. So basically the structure are less clustered and everything is smoother. This in turn quantitatively can also be measured by counting the halos that live in these different scenarios. So here is the halo mass function. So basically it's the number of halos as a function of their mass. So different lines belong to different models, and you see here with the ratio that the different models predict a smaller number of small halos can be 20 or 40% different from a perfectly cold scenarios. And moreover, what I want you to notice that this difference among the models are higher at higher redshift. So higher we look at, bigger will be the differences among the models. So again, to give you a picture of what is going on, if this is a filament in my cosmic web, so the structure of the overall structure of the universe, here I've identified some halos in a cold dark matter scenario, for instance. But then if I look at the same region of the sky in a non-cold scenario, it means that there are some small halo missing. So maybe I give you an idea of why this will make a difference at the epoch of organization, because this first galaxy live in these small halos. And so if I have a suppression of low mass halos where these faint galaxies live, then I will have a different contribution to overall ultraviolet budget of photons reionizing the medium. And probably then I will have a different ionization history at play. So of course, we were not the first thinking about this. So many people have already explored what this epoch can tell us about the dark matter, but of course it's hard really to disentangle what is going on with the low mass halos together what is going on at the baryonic level of galaxy formation. We don't understand galaxy formation. We understand even less galaxy formation at these high redshifts. So we wanted, in this work, we wanted to do something which was agnostic of the whole galaxy formation issue here. So something that we didn't need to take into account and know what was going on with these first galaxies. And so this is what we did. So we started from data. So this is an example of galaxy luminosity functions as measured using these Hubble deep fields that I was telling you before at these redshifts. So we can, there are some data already at redshift 10. not many data points, but this will keep improving if we think about the James Webb Space Telescope and so on. So it's really a promising area of research here. So for people who are not familiar, here is the number of galaxies as function of the UV magnitude. So as we go to the right is the faintest galaxies here, and on the left is the most luminous ones. And so building on the work done by these people that run very high resolution N-body simulations with different dark matter models, we calibrated these luminosity functions against the N-body simulations in a really detailed way. We corrected for dust extinction, and then we could link this luminosity function together with the star formation rate. We did this in a fully probabilistic way, so we didn't link one-to-one this relation, but we also accounted for some scatter and so on. And we did so for data sets belonging to lower redshift, where we actually have more data. So once we calibrated this, we fit it against the data at higher redshift, as I'm showing here. And basically, you can see that this different, I'm showing here for 4 different models, their difference show up indeed at the faint and region of this plot, and their difference are higher as we go higher in redshift. So basically, now we have a set of luminosity function that that is predicting that it is, they are telling us the number of these sources at the redshift, which are important, I mean, where the EOR started to happen. And once we had this in mind, we could predict the whole EOR history. And we did so with this really simple model here that many people have used so far, is the most simple one. So basically, how the ionized fraction changes with time is just function of a source term, which depends on the amount of ionizing photon that is emitting this rate here, and the sink term, which is due to the typical time which these photons can actually, not the photons, sorry, the ionized can actually recombine and become neutral again. And here the point is this n dot here, this emission rate, that is actually a function of this luminosity function that I was telling you. So with this at our hand, we could predict this n dot, but we also needed these 2 extra parameters, the escape fraction, so how many photons are escaping from the galaxy, managed to escape and get and go through in the intergalactic medium, and also the limit on magnitude at which this function here should stop, because we actually don't know how far, which is the faintest galaxy that actually existed out there. So with this at hand and playing with these 2 parameters, we could predict different reionization history. So in practice, what we did, for instance, here is tau, the integrated Thomson scattering optical depth from the CMB. So here you have different panels. It's always tau as function of redshift. Highlighted is the latest Planck results, and you see with the different curves our reionization history. And you see, of course, that again the differences arise for very faint, like when I allowed my luminosity function to reach very faint limits, like here and then on the first row. And from left to right, and also varying the escape fraction. So again, when I allowed more photons to manage to go out to the galaxies, I see most of the differences among these models. And so actually, just alone, the Thomson scattering optical depth can tell you, I mean, in this case, for instance, the cold dark matter is ruled out compared to the other models and so on. So the Thomson scattering can really tell us something about it, but most of the time, all the models seem to agree with tau, and we cannot really tell these models apart. So we started by adding other data points to the picture. Isabella? So here is, yeah.
You have 1 minute.
1 minute. Okay, I will need to be fast. This is with the data points of the neutral hydrogen fraction. And so the main point, I need to go fast. The main point here is that most of the time, either all the models are excluded or they all agree with these data points. So basically, most of the degeneracy comes from the parameter themselves of the EOR. We added more CMB data. So for DPSF, they show us how in 2016 in this intermediate release, they try to constrain the duration on the y-axis and the middle reionization redshift with the CMB Planck CMB data by assuming some models. And again, here I'm playing around with these two parameters, and the picture is the same for all the models. It's really the parameters like the limit to magnitude and escape fraction that tell us which reionization history should be more closer to the truth. Again, with the SPT data, so here they are assuming some models and using the KSC inferring these limits. And we also try to let the escape fraction vary within some data points that we also have on this plot here, but we didn't find any strong difference again. So we tried all we could basically, but the bottom line is that the limited magnitude here and the escape fraction are the ones that are really degenerate in order to predict and to tell apart the different dark matter models. Here is just the parameter estimation that we did just using the Planck tau, and on the bottom how these constraints actually shrink when we add the information on the neutral fraction. And we see that basically, so this is in agreement also with other totally different works, so which is good news. And so basically the bottom line is that current bounds on EOR are largely insensitive on the underlying dark matter scenario. But what we found out is actually that the Pliesta EOR model with our calibrated luminosity functions inferred curves is perfectly fine in order to reproduce all the data that is available at the moment. And one thing that I want to point out is that in most of other works, people find a lot of difference between these different dark matter scenarios because they assume the same galaxy formation is occurring in all these different models. But actually what we found out by inferring this luminosity function with real data is that the galaxy formation cannot occur in the same way in all these different scenarios. So this is something that we need to keep in mind. And I am done. This is all I want to tell you today. Thank you for listening.
Thank you very much. Any question for Isabella? I think just a comment. I think from your plot on the luminosity functions at high redshift, I mean, if you really want to make the difference between your different dark matter models, that's where you need to have new data more than reionization or something else, no? If you happen to have a low luminosity galaxy at Z of 10 and you can count them, if you have enough, you make a stronger constraint. Oops, sorry.
Yes, I agree with you. The strongest constraints for the dark matter will come from this luminosity function data. Yeah, because even looking at, for instance, here, KSD constraints from the SPT, really what makes a difference are the EOR parameters, not the dark matter models we live in.
Mm-hmm. Yeah.
So even if we improve these, but we will learn a lot about the escape fraction,
okay.
And in a way also about how far this we should push for this galaxy luminosity function to go on, where they stop.
Okay, thank you. We can now move to the last talk from Stephen Benton. Hi, Stephen. And Taurus, Barenboim perimeter for cosmic reionization. Yep.
Can you see my slides?
Yes.
Oh, that's the end.
That was fast. Okay, anyway, you have 15 minutes. Thanks.
Great. Hi, everyone. Thanks for having me. I'm Stephen Benton, a researcher at Princeton University. We've heard a lot of talks in this conference about focusing on predictions for the big ground-based observatories and the big space telescopes. I just want to represent the little guys a bit. and especially the balloonatic's that put their telescopes in the stratosphere. So in particular, I'm going to talk about a new experiment in progress called Taurus. And we want to measure the large-scale E-mode polarization with this. And we will planning for a mid-latitude balloon flight, which I'll say more about a little bit later, with a cryogenic hold time of up to around 50 days. Looking at the current landscape of CMB observations, we think the main ways that a balloon can contribute compared to things like Simon's Observatory and CMB Stage 4 are providing information at high frequencies and large scales. And those two lead then fairly naturally to the study of the low L reionization feature in the EE power spectrum. So just as another quick review here, as the optical depth of reionization increases, this feature at the small L region of the power spectrum increases in amplitude. And then there are also, depending on the details of the history of that reionization, some shifts in the peak and shape, which are harder to detect, especially when you don't have overly dramatic changes like I'm plotting here. We don't, unfortunately, at this point have detailed models beyond just the simple average optical depth. And that's been our focus, partly because the average optical depth is important for breaking degeneracies with the amplitude of scalar fluctuations on small scales, for doing things like constraining the mass of neutrinos with CMBS4. So this plot is just showing that the noise in your map stops mattering at some point on small scales if you can't constrain tau better on large scales. And so we hope to be able to help with that. Taurus is the latest in a family of CMB balloon telescopes. And I'm showing the most recent to fly here, which is SPIDER. And Taurus inherits a lot of the lessons and technology learned with SPIDER. As a unrelated topic, we published our B-mode results last month, so I just wanted to plug that briefly for the first flight. And I'm showing here temperature maps, SPIDER compared to Planck. And you can see that on large scales, we agree well. And the Planck map here has only been modified to remove the overall mean of the map in this region. But otherwise, everything kind of agrees. The problem SPIDER has for probing reionization is that flying from Antarctica, the sun is up all of the time. And so there's only about 10% of the sky visible if we point away from the sun and avoid the galactic plane because we can't do CMB science there. And that's far too limiting to be able to do reionization. And that leads me to a bit of a talk about the balloons themselves. To fly a 3-ton payload like SPIDER to 35 kilometers in the stratosphere takes a lot of helium. So we have these very, very large balloons. And I've added an international size reference here as well. Let's see, so in addition to the fact that these are huge, the balloons on the left here, you can see that on the ground, it's only a tiny fraction inflated because it's a factor of 200 to 300 pressure difference between ground and at float. So there needs to be a room to expand. The worry is if you put too much gas in that your balloon might pop as it expands. And the way this is dealt with for conventional balloons is that the bottoms are open and gas can escape. The problem with letting gas escape through the bottom is that every day, if you have the sun setting and rising, you will lose gas every morning as it expands. And this really limits the length of flight that you can have, which is why, for example, SPIDER flies from Antarctica, where the sun is up all of the time in the summer and the diurnal variations are relatively small. But to do this large-scale measurement that Taurus wants to do, we need to use newer technology with so-called superpressure balloons. These are not open at the bottom, which is harder to avoid popping, which is why it's newer technology. But it means that they can maintain very stable altitudes, even at middle latitudes where there are true day-night cycles. And this means with an experiment like Taurus, we can observe all night and see the entire southern sky. So this is really a critical enabling technology. So it's required in balloon talks to have at least one slide showing how horrible the atmosphere is. And this is my one here. And so the reason we put our telescope on a balloon is to get above the atmosphere. And this is showing the Spider and Planck high frequency wave bands as compared to emission either from the South Pole or from the stratosphere above Antarctica. And you can see that from the stratosphere, the atmosphere is orders of magnitude dimmer. And this does two main things for us. First is with much lower backgrounds, we can have more sensitive detectors. And this is how, with order of months of observing from a balloon, we can compete with years of observation from the ground. But for these large-scale organization studies, the other important factor is that drifts in the atmosphere represent one of the main large-scale systematics that have to be dealt with to accurately reconstruct CMB on the very large scales. The other feature that you'll see here is that so ground observations usually occur in these deep windows between molecular lines where the atmosphere is relatively dimmer, but at high frequencies, there just aren't options that are as good anymore. And so this is why TORUS is focusing on these high frequencies, and the four highest bands are essentially the combination of the four highest Planck and Spider bands, and we'll have 10,000 detectors between them. The reason we need these high frequencies, much higher than optimal for looking at the CMB, is to separate the foregrounds, which are the other big problem we deal with on large angular scales. So you can see here the expected CMB signal in black as compared to colored dashed lines for the interstellar dust foreground. And so the dust is dwarfing the CMB signal, and so we need a factor of 10 to 100 in cleaning. And this is why we want these very high frequencies with very high signal to noise measurements of the dust to give us reliable measurements to clean the CMB signal. At lower frequencies, the dust will drop, but then synchrotron starts to dominate, and you just can't win anywhere on these scales. There will always be a foreground that is larger than the CMB that you're looking for. And with TORUS, because balloons are better suited to this high frequency observing, we've chosen our lowest frequency band to be one where the synchrotron still contributes negligibly. So the one other big concern, aside from foregrounds that are irreducible, is instrumental systematics. And aside from the atmosphere, there are sort of many other things that can affect these large scales. One example that I illustrate here is scan synchronous noise. So if you have anything that's kind of quasi-stationary, but not fixed on the sky, it can be hard to distinguish from the true sky signal. So these are simulations using the spider pointing. And if we inject the signal with no correction, we end up with something on the left that is significantly contaminated. And there's sort of large scale noise features that we need to remove. One of the things TORUS does is it takes its separate telescopes pointing out of the cryostat here, and they're offset in azimuth, so that as it spins, the sky signal will be out of phase. And just this mitigation alone is enough to totally clean the scan synchronous signal when we make this map on the right. Further compared to Spider, TORUS has much more rotation of the sky because it's not flying close to the South Pole, and its scan strategy will be more carefully optimized to be able to reconstruct these large-scale features that can be difficult without scan crossings. And the scan strategy, when you have the sun down and can observe all night, is really simple. TORUS has a fixed elevation and just spins around constantly at fairly high speed. And then as the Earth rotates, this circle kind of translates across the sky over the course of a night. And then there's a little gap where during the day we can't observe anymore. And that's what this looks like. In total, we see about 70% of the sky. If we cut out the 30% or so most contaminated by the galaxy, which is the green outlines here, that brings us down to about half the sky that we have left, including kind of all of the clean southern galactic hemisphere and half of the north. So on the hits, or on the left, I'm showing a hits map here, and on the right is a polarization statistic where just being close to 2 means we have enough angle information to reliably reconstruct the polarization here. And so then just to kind of wrap up, this is a projection of how well we think we can do compared to Planck. So the horizontal line on the top is the nominal Planck 2018 limit. And we show here what torus can do as a function of the largest scale, the minimum multipole it can reconstruct, both for a 7-day flight and a 30-day flight, and for a couple cases of the amount of sky that we can reliably clean from foregrounds. And so with even a week of data, if we can construct below L of 8, we can start to beat Planck. And with a full 30 days and L below 16, we can get within a factor of 2 of what is essentially the cosmic variance limit here. The red dotted line is kind of an impossibly good experiment with, you know, S4 level noise and resolution, but perfect cleaning over the full sky. So that kind of represents the ultimate limit of what's even conceivable. But we think torus with 30 days will come close to what is practically possible in terms of further constraining the signal. So we get, you know, a factor of a few reduction from Planck and a factor of 2 to within what's possible to do at all. And yeah, I kind of removed most of the instrument details for this audience, so that's torus. So thank you. Are there any questions?
Thank you very much. Any questions? There's one question. So what the question from Gail was, what is the lowest L anyone has ever done with a balloon? Largest sky fraction.
So like I said, the largest sky that you can observe from a long duration flight is around 10%. You just can't observe more than that from Antarctica. There are experiments that don't fly from Antarctica, and then they're limited to 1 or 2 nights of observing, but then they can kind of observe the full sky. There's an experiment called Piper doing that. They've had 1 flight to date. I don't think they have published results yet, so I don't know how low they've been able to go.
But I remember Archeops did like 30% of the sky. Mm-hmm. But the galaxy was in the middle, so it was not like 30% useful for CMB part. But and can you remind me, maybe I missed it, the beam size of?
For torus, we'll have degree resolution.
Degree resolution, okay.
Yeah.
And if just may as well, so you choose 4 bands. Do you think it's feasible to have a smaller bands but more bands to remove better the dust and the synchrotron? Or is it not feasible?
The real problem there is we would lose. We're kind of at the limit of what we can fly in terms of power and readout with 10,000 detectors. So smaller bands would just mean kind of less total signal when we're detector limited.
Okay. Thank you. Yeah. Thanks for this round around torus. So I propose that you'll leave us like 1 minute to move you all as panelists so that you can all speak for the discussion session. And then we can start just after that discussion. So one by one, I will promote you all as panelists.
Just quickly in the chat, someone asked if we have a launch date scheduled. I kind of breezed past that. We don't have a schedule. It's very hard to predict balloon dates far out, but we're hoping for 2026. So a little bit before Lightbird.
Thank you. almost there. Okay, so we are now all panelists. So you are allowed to speak and give your thoughts. So first of all, is there any points you want to raise as a discussion point in the? So let's say that we have like half an hour discussion if you want. Is there anything you want to bring up to everyone and discuss? If not, we have some. Yeah. Nope.
Well,
So,
this is
yeah.
Salim speaking. I don't have a specific point. What I missed in the talks is, kind of most of them either focused on KSZ or reionization separately. I think Gil has kind of this comment also in the email. But the cross-code talk between the two fields of this was a bit missing, for good reason, as we know. But at least that should be discussed a little bit.
Mm-hmm.
I think it was the point of that's sort of why we wanted to organize this as well, is to try and bring everyone together, because these events don't happen very often, at least to my knowledge. So it's a good occasion to discuss it.
Yeah. Any other thoughts? I mean, we can start like that on that, and it's true that for now what we've seen is that separate studies of the IL and Lowell CMB data, focusing or on KZ or on like typically the EE bump at Lowell. I think it's also driven by the fact that experiments are specialized in Lowell or IL, depending on the ground or on space. But obviously, the two hands should tell the same story. So that I think we are just at the time where we have good data on both ends. So we should really try to do all things all together. And the related question is that should we continue using the power spectrum or go back to the images? And what are your thoughts about this next points about? We've seen some talks about trying to reconstruct the image of the KSZ, the maps, instead of using the power spectrum. Is it the way to go to have more information, and will we get the same information? I don't know.
I mean, those 4-point estimates definitely have more information in them about, you can actually, so Simone was talking about that. I don't know if he's on. So there definitely is a bit more information in there, but it just seems like for a while, at least, that's going to be pretty noisy.
Mm-hmm. Yeah. Well, is the noise is the noise the only limitation, or do you think we would have like? We should think about foregrounds and systematics as well. We didn't discuss much except the last talk about observational limits, but the reconstructions we've seen are or perfect or just with some white noise, if I understand. Will we be limited at IL by systematics or foregrounds even before being limited by noise?
Well, that's a fair question. So I think a lot of the forecasts that are now being done for S4 and for the SPT3G and SO do assume that you have to at least do some frequency cleaning to try to get nice clean KSE. However, if you really want to get like if you start projecting out components, it gets pretty dirty. And then the CIB just seems like it's just a bare. And the CIB has a lot of non-Gaussianity in it. And so I feel like there is eventually going to be some reckoning where people doing CMB, KSZ reconstructions are going to have to wrestle with what the CIB is doing.
Mm-hmm.
But I don't think we're there yet.
Okay. In the same trend of my question about Taurus, I mean, do we think that having like much more frequency bands instead of a few will really help cleaning these foregrounds? Because most of the current
I mean that's the experience with the 21 centimeter, right? I mean, the more is frequency, the more you have leverage over the different the more frequency information you have, the more leverage you have in order to utilize the different frequency dependencies of all kinds of things. So that certainly will help, but you end up with less signal to noise per frequency bin. And so I'm not sure. I haven't thought about this from the CMB point of view, because that's one of the issues always, that you try not to have too many of those frequency bins because of the noise aspect, I guess. But maybe it's also technologically more complicated. I actually don't know.
Any specialists of IL CMB measurements?
But it certainly would help if you have more bins in terms of frequency, because then that gives you more leverage to in order to fit the different dependencies on frequency and kind of basically clean things up. It gives you another direction.
So, related to that, we see the evolution of CMB experiments going to many detectors on the ground, and it's going quite fast with advanced ACT, SPT, or SPT3G, or whatever, S4, SO. On space, there were several missions planned. There's less now, but obviously they are targeting different scopes, but most of them are for the space part are targeting the B modes, but you can have like realization for free if you go to really low L. And I was just wondering if how you're feeling about the target, or the best promising part would be like large L or small L for realization, given what we just said, that we have to consider foregrounds, we have to consider how easy to beat the noise or not.
I mean, go ahead.
No, go ahead, please.
I mean, I was going to say, I mean, I'm obviously quite biased because I'm involved in high L more than low L, but to me, it seems like there's more room for improvement at high L, that the power spectrum error bars can go down a lot more. These 4-point estimates will only get better as the data gets better. Whereas with high L, we're talking about sort of factor 2 improvements is the best we'll ever get. So it just seems like there's more room for improvement. So that's where I would go.
Will it bring more information on the epoch of realization itself? Or?
No, I doubt it.
Well, more than the low L.
Yeah.
There's not that much information at low L, right?
Yeah.
So there's kind of what, two, there's another number, there's tau and something about how it happened, but it's even with tau being so low, it's hard to even get three numbers from the low L.
Yeah, I mean that's true, but there are more contaminants at the high L things, right? The clusters become an issue, and so I mean, as long as you have a handle on all of these things, there's another thing which is the silk damping basically kicks in, and so there's a limit to how much you can do with high L. In terms, I mean, I remember that's what limited us when we tried this to do long ago, this cross correlation between 20 centimeter and kind of KSZ, if you remember, Marianne.
Yeah.
And when you get hit by the silk damping. Silk damping happens on scales where things become interesting, and then CMB gets down, whereas 21 centimeter gets up. Yeah. So I guess the answer is a bit complex. It's not just. And the other thing is that if you have very high resolution, you might have also. Yeah, maybe I'm wrong here, but let me say what I was thinking is that if you have very high resolution, then high Ls, then you also get many independent bins along the line of sight with different velocity kind of component, and that might be wiped out because again the information is carried out by the velocity, and the velocity has a certain correlation length. So going way beyond that correlation length might help you, but I don't think it would help you a lot. But yeah, I might be wrong here. I'm not sure.
I mean, a bigger question I have is, and this is probably more for the non-CMB people that are here, is where does CMB data fit in the broader reionization community, like compared to the luminosity functions in 21 centimeter and the absorption lines? Like, how much better is that data going to get in the next few years?
Well, I come from the 21 centimeter community, Gil. It's a challenge. It has been a challenge. We have been at it for about 2 decades now. It's really a very difficult measurement, and we are still struggling with basic things. I mean, if I want to compare the situation in this field, at least, not in terms of the galaxy surveys and kind of Lyman alpha emitters and things like that, but the 21 centimeter itself, redshift 21 centimeter measurements, it's kind of pre-COBE type of situation with the CMB. It took something like 20 years, 30 years to get to COBE from the initial things. But we are roughly there. The calibration has been kind of an issue, but things are improving. There is lots of improvements in the old ones, in the kind of some experiments that have been going on for more than a decade, like LOFAR, but also there are the new ones like HERA, and that are giving kind of much higher upper limits now, or much better, upper limits. So we are getting there. It's still a slow game, but we are getting there.
But would there be any role for CMB if 21 centimeter gets to where it wants to be?
I think there will. I mean, there will be. So far, we look at it as one number. I mean, the tau gets into all of our estimates. But the CMB will never have the same kind of constraining ability that the 21 centimeter have. If we get our act together, I mean, well, if we get to try it, let me say it this way. Just because of, as you said, it's a blunt instrument, it's tau that you are sensitive to, and that's about it. And you have so many other kind of constraints. So I think it can give a little bit, if it improves a little bit more than now, the constraints from the CMB, they will help a lot. But so far it has been helpful, right? Because that's where we it has been helping focusing our effort where to look for and which frequencies and to redshifts to focus on. But beyond that, I'm not sure. Actually, that's my experience with this.
Mm-hmm. So does anyone have any comments about what JWST is going to do for reionization?
luckily, they will improve the luminosity function at high redshift.
But it will be still be these higher kind of
and it's very
these massive halos. But it certainly will improve things quite a bit.
But people looking at lens galaxies behind clusters are already like pointing towards the same redshift range as GWST will be doing. So we kind of have a first glance of what GWST will do. But I don't know how, I mean, I don't remember any forecasts about the precision, and if we come back to the plot that Isabella was showing, how much it will improve the high redshift part. And about quasars at the end of the reionization.
Well, those have been improving, but there aren't so many of them. There's recently has been a report of a radio loud quasar, which is very interesting at high redshifts. Those are promising for 21 centimeter forest type of measurement. So if you have a number of those would be very clean kind of measurements of the 21 centimeter, provided that the temperature of the IGM is not too high, because otherwise you wipe out the effect of the forest or make it weaker, actually, at least. Yeah, I mean, that would be nice, but so far there's very little of this, I think. And just it's a very difficult measurement, these things. But also the ones that they have been discovering at redshift 7 that are radio quiet are very interesting, in the sense that they tell you about, the proximity effect gives you all kinds of constraints about the condition of the IGM at these redshifts, but you can't go too far with that, I think, with the current instruments. So yeah, so this also has been a very slow progress after the big kind of thing after Sloan. This has been a very slow process of getting more and more quasars of this type.
And it also get up and downs, but by sometimes we were sure that the reionization was ended at Z of 6, for example. And now every time we look at the new quasar, there's fluctuation in the kind of end of the fluctuation going back to 5.5 or 5.3. So having only a few line of sight is I mean, it may be enough for the mean history, but it may also show the variations of history of reionization depending on the line of sight. For the broad history, we need much more, I think, that we have now. So what are the other probes of reionization that we didn't discuss?
There's the intensity mapping of other lines, right? That was briefly mentioned by Gabriella. Thinking Lyman alpha, forest, etc. But I don't know if anybody knows more about this than us.
I don't know much. And something that you mentioned, Salim, is the cross correlation between different probes, and we didn't see much of that in the 2 days. I mean, there are a combination of probes in the same MCMC, etc., but not necessarily a cross correlation of signals. I mean, what we tried on SK or predictions and Planck was a bit hard, but maybe there are clever ways of doing that, and maybe also at higher moment. I mean, tree spectrum or things like this may enhance some signal. I don't know if anybody is looking at these kind of things right now, like KZ for the CMB cross 21 centimeter or cross intensity mapping.
I'm not aware of anything is going on in that direction. As I mentioned, we tried this with Vibor Jelic long ago, and Hiroyuki, if you remember, Marianne.
Yeah.
And it just it seemed not very promising then. But maybe there are better simulations that can address this, but I'm not aware of any work in this.
Okay.
Maybe others have. I see Harold there. Maybe Harold knows.
Just exact cross correlation between CMB and 21 centimeter. I think some other work has been done after Vibor, but it's been a while.
Yeah, but it's not much though.
I guess the problem is a little bit that, I mean, we don't have 21 centimeter observations yet. We sort of have K at Z. I'm not sure how. We're quite far from any intensity mapping of some of other lines in 21 centimeter. I don't know, did somebody mention the Lyman alpha emitters yet? So that's this other, right? It's one of these points that people like to use in these reionization history plots. So it's this measurement of the neutral fraction based on the fraction of Lyman alpha emitters dropping around redshift 7. I don't know if there's been much progress there. The only thing I know is that they're finding Lyman alpha emitters now also at redshift 9. They're a handful, so they're probably very special objects, so we don't know if we can. But I mean, it's not that they completely disappear. The fractions seem to go down beyond redshift 7, but then I guess naively we would expect that by redshift 9 there would be nothing left, right? The universe would be so neutral that none of the Lyman alpha comes out of any galaxy or reaches us from any galaxy. But that apparently isn't true, which I'm not entirely sure what that means. I mean, it must mean there are large enough H2 regions present at redshift 9 for the Lyman alpha to be able to escape.
So if there is H2 at redshift 9 and there is neutral at redshift 5 in some line of sight, different line of sight, is there any things that predict so much difference in the history of reionization depending on the location? Is it so patchy? Do you see in simulations so much difference in different places?
I'm not sure if we can answer that in the most general sense, but it's like the question I saw about having the flat bottom profile from edges. I mean, if you can play with your galaxy parameters, then you can produce anything you want, I think. So then the next question is how realistic are those models?
But we can say something generic, Harold, that it is patchy up to the scale of kind of roughly 100 megaparsecs. That's something that we've seen in simulations, right? I mean, unless it's ionization is done by X-ray or something like this, then that's not the case. But if it's done by normal UV photons, then which is what everybody thinks, then there's a natural scale there, which is the scale of bend over of the turnover in the power spectrum, which corresponds to the scales of voids and which is about 50 to 100 megaparsecs. So that we see in the simulations. That's I mean, Harold and I use this to claim that you can do imaging even with these very low signal to noise experiments like LOFAR and other experiments. Now LOFAR can't do this, but it's not beyond that. It cannot be too much beyond that, I think.
The interesting thing is, though, I guess going back to Marianne's question, is that it's not symmetric in some sense. So that if you go back to the end, if you go to the end of reionization, the remaining neutral regions tend to be quite large, extended in size. They're low density. They're not much in density. They're the low density areas, but they're quite big islands, as we like to call them, neutral islands. Whereas if you go to the beginning of reionization, I think most models will say that the H2 regions in the beginning are tiny, tiny. So if you go, let's say, to 1% reionization, you'll have many extremely small H2 regions and maybe only very few big ones. But if you go to 1% neutral, you'll have quite few, but relatively large neutral islands. So it's not, in that sense, the process is not symmetric, and that may help. Although I think for the Lyman alpha emitters, you need a big enough H2 region built by some sort of protocluster in order for the line to be able to escape. For the patchiness in the transparency, this Lyman alpha forest transparency at the end of reionization, I think we can, that is easier to understand in some sense, because you get fairly large regions that remain neutral, because that's sort of the typical size of the voids, which is the size that Sally mentioned.
So ideally, if we can measure the correlation length of these bubbles with redshift, we can learn a bit more about the processes, I guess. I mean, at least check that we see the same thing as the simulation sees. Okay. Great. Any other points related to? So we didn't see much forecasts of future CMB emissions, but I think they are hidden behind the B mode search. But okay. One funny final point I may mention is that we've seen delta Z a lot in these different talks, but with all a different definition. Could we kind of agree to make one definition and call the other one differently?
Good luck.
No, I mean, yeah, it's better to specify it every time, but I don't know if there's a physical definition, not really, but I know for the cluster part, there's like this degeneracy between sigma 8 and omega m, and now everybody is using big sigma 8, which is sigma 8 omega m to the third, which is kind of the degeneracy we see in different cluster thing, but it depends on redshift, so it's never 0.3, but still there's like a common definition which is used, which may actually I don't really like, because it's like not necessarily fitting the data itself, but let's see that at least we define it correctly, not correctly, but we define it every time we talk about it, because you never know if it's like from 5% to 95% or to 45 to 55, and it's a big difference. Okay. I think it's, well, it was 2 intense afternoons. I mean, afternoons for us, sorry again, for those for which it was too early in the morning, but it's hard to make a remote conference with everybody around the world in the same time. So thank you for participating and giving talks and having questions. Remind you that the full SAZERAC meeting will happen on the 14th of June, is that right? Yes. And if you want to submit abstracts, it's kind of today. And so I really enjoyed these two sessions. I hope you did. maybe to do it again another time. Hopefully in real life, because it's like a bit painful to not see each other and not to discuss really. Hope everybody is fine. Keep safe. Take care. And talk to you soon and somehow, somewhere. Hopefully. Bye-bye. Thank you again.
Bye.
Thank you for
See you.
coming.
Thank you. Bye-bye. Thanks,
Bye.
everybody.
Bye. Thanks.
Bye.
Si, à plus tard, Adélie.
Ouais. À plus.
Ah non, je sais pas, oui. Faut que tu éteignes le YouTube avant que...
Oui, je le fais.